So this is an example. What I've done here is an example of the way that people are going with fork diagrams now is trying to extract as much quantitative information as they can. Clearly, in this sample, we have a mixture of domain states. We have different things going on. We have vortex states. We have some maybe single domain behavior. And we're trying to develop more sophisticated ways of approaching this idea of trying to quantify what different states there are inside your sample. And we showed, there were some examples yesterday of where people have attempted to do this, looking at the volume fractions of different phases in their sample. So I'm going to show you, using this type of sample, a method of how we can sort of pull this signal apart. If we have a suite of samples that have been made in the same way but vary subtly in terms of the proportions of different phases that they contain, then we can actually use multivariate statistics to pull apart those variations and get a much better feeling for what the different phases are that are present in your sample, and actually get a quantitative estimate of the proportions of those phases. So I'm going to illustrate that with this example. Okay, that's not hiding itself. Let me just quit that. Nope. Okay. So you were asking about the batch processing option. Well, that's this button here. Load multiple forks. There you go. So it exists as a feature in this software, but not in FORCel yet. Okay. So I've done the loading and I've done the processing. So what I've done is taken 6 samples these are all made by Sophie. So they're all the same sort of sample, made in the same way, but they're all subtly different in terms of the proportions of different phases that are present. So what you would do to analyze them is you would organize all of your data files into a folder. You would click this button here. It would ask you to locate the folder, and it will then import all of the files that are in that folder, and it will ask you a series of questions about what processing steps you want to do. Do you want to extract the central ridge? Do you want to remove the first point artifact? What smoothing factor do you want, etc., etc.? And after you've answered those questions, it will just churn through, load in all the data, process it, and it will dump the results into a 3-dimensional stack of processed data, which is here, which you can zoom through now. Okay, so these are 6 individual samples, all showing similar but subtly different fork diagrams. Okay, and the intensity scale is only optimized for the first one, which is why you don't see all of the details in the other ones. But they all look pretty similar to each other, but they are kind of just subtly different. Okay, so that's a 3-dimensional data stack of several fork diagrams, each one representing a different sample. Now, to run this statistical analysis on it, what we do then is we define the region of interest in this fork diagram. So I'm interested in signals from around minus 0.4 up to about 0.05, and from 0 up to about 0.6 Tesla in coercivity. And what we do is we resample that fork diagram on a grid of points that sort of capture all of the key features that you're interested in. So what you would do is click PCA grid, and it will ask you for what region of the fork space do you want to resample. So we want to go from minus 0.4 in HU to about 0.05, 0 for coercivity up to about 0.6 Tesla, and I'm going to do this with a fairly low resolution just to make it fast. Okay, that's 20 millitesla. Okay, so it resamples that data on those specified grids, converts the data into 1-dimensional data, and then organizes it into a matrix. Now, you don't really need to see these matrices. I'm just going to sort of delete them. But what you see here is 6 essentially 1-dimensional fork diagrams now, arranged, stacked on top of each other. Okay, but you don't really need to see that. Okay, close. There we go. Okay. So you then click the Run PCA button. And what it will do is it will analyze using just standard principal component analysis the variations from one fork diagram to the next. And it will then say, well, can I explain the variation between those fork diagrams using a number of principal, kind of fundamental fork diagrams or principal components? And you get this table, and this table tells you what percentage of the data variation in your data set can be explained by a given number of principal components. So if we look at the top, we say 68.7% of the variation from one fork diagram to the next can be explained by a single principal component. If I have two principal components, then I can explain 91.6% of the variation in my data. If I have three principal components, it's 97%, 4 gives me 99%, and I can explain all of the variation in my data with 4 principal components. So you then have to decide which of these do we think are important and which ones aren't. So the first one is obviously important. The second one is actually quite important. That's over 20%, 23% variation explained by the second principal component. So that's probably important. The next two are probably noise. So I'm going to just look at the first two principal components and see how much can we explain of our data variation with just those. So I select 2 here for the number of principal components that I'm interested in. So it's just going to use the first 2, and then it'll plot a principal component score plot. Okay, I'll get rid of that table now. Okay. So what that brings up is, first of all, this little window. This is a calculated fork diagram based on my position within this fork plot, with this score plot. Okay. Now, if I move the cursor around, you'll see that fork diagram updates. Okay. So what we're doing is, I guess I can show the equation. This was on, where is it? Okay. Is that the one? Yay. Okay. So in terms of equations, we can our sample is the average fork diagram plus a principal component score times this loading vector. And this loading vector is essentially equivalent to a one-dimensional fork diagram. Okay? So it works out these loading vectors and it works out these scores. And any fork diagram can now be described as the average fork diagram plus a PC score times this vector plus a PC score times this vector. And some error, which will be mainly noise. Okay? So what that means is we can go anywhere in this fork plot, in this score plot, and calculate from that equation what the fork diagram would look like. What that allows us to do is kind of explore around, see what the different M members might be. So the most important principal component is the first one, so that's along the horizontal axis. So if I go along here, okay, I can see how the fork diagram evolves. And what we start to see is that we get something that looks very much like the pure vortex signal, this kind of butterfly signal with a strong signal here. It's where that little lump was in the coercivity distribution. A negative signal underneath, and this signal here. There's also a little hint of maybe a signal right around the origin there, which might be low coercivity material. Okay, so that looks kind of like the vortex state. If we go this way, okay, we start to see something that looks like classic interacting single domain, or maybe slightly pseudo single domain, probably interacting single domain. With a much lower coercivity and the positive-negative signals that we've seen. Okay, so these are all realistic-looking fork diagrams, and our samples can now be explained as a function of those, as a mixture of those. Now, if I go up and down, I can see how the fork diagrams relate. If I go down, I see this little small signature here increasing. Okay, if I go up, that disappears. So if I go to, say, somewhere like here, I get something that now really does look like pure vortex state, right? Because of the pure vortex shouldn't have a signal here, and now it's gone. Okay, but if I go down, then that little signal comes back. Okay, so I'm just exploring the space and trying to interpret what we see. But to me, that looks like, okay, that's a pretty reasonable, physically realistic-looking vortex state. So I'm going to say, okay, let's call that our first N member. So click on here, It'll bring up a window. It's not really important. Let's do that. So I've defined this as, say, an end member, which I think is very close to a pure vortex signature. Okay, then I'm going to go along here. Okay, just optimize the intensity. Okay, somewhere around here. If I go too far, I start to get negative signals here, which are unphysical. So I know I've gone too far. If I go along here, I get something which looks exactly like a weakly interacting, low coercivity, single domain type signature. So I'll just stop there and call that my second end member. No, it brings that window up again. Okay, go away. And then I'm going to say, right, well, when I went down, I found this low coercivity thing. Okay, so I go way down here. Maybe move this up a bit. Ooh, okay. It's getting a bit too much negative here. That looks unphysical. But around here, okay, we're getting signatures which are a very low coercivity, possibly close to superparamagnetic kind of signature. So you might have some really small particles in this material. Let's call that our third end member. Okay. And then calculate proportions. Boom. Okay, there we are. 1, 2. Oops. Yeah. Oh, go away. 3. And proportions. Okay, so what it's done now is surrounded the data by a little triangle. Here's our first end member, our second end member, our third end member. That's what the FORC signatures that each of those correspond to. And then these are the proportions worked out from the coordinates in the score plot of each of these individual FORC diagrams, what the proportions look like. And then we can then physically associate this where we've got some pure vortex states in our sample with this very high coercivity ridge and the negative, and then this nucleation annihilation signature. We have some interacting single domain particles in there, and then we have possibly some very small, close to superparamagnetic type signatures in there. So just from those 6 samples, you can explore this space and sort of tease out these different signatures and actually turn them into a quantitative measurement of what proportion of the irreversible magnetization in your sample is explained by each of these components. Okay. Yeah, question.
Here you suppose that there is no interaction between.
Yeah. So the inherent assumption here is that these are independent components inside your rock, and this is a good assumption for most rocks, where you have like a mixture of this mineral and this grain population and this grain population. But of course, as I showed yesterday, if you have two minerals and they're not interacting, then they're linearly additive in the FORC distribution. But as soon as you have strong interactions, you get additional signals which are not. Yeah. So in the basic assumption here is that the FORC signal can be explained as the linear combination of independent populations of signatures that are not interacting with each other. Yeah. So if anyone wants to know more, talk to me or No about that. Hopefully, if the paper gets accepted, this will be released shortly. Okay.